Welcome to the lecture series on CFD Part 1. This is Lecture 4 on Introduction to Finite Difference Methods. We start with an explanation of principles of finite difference methodology and continue with an introduction to approximations of derivatives using Taylor series expansion. This approach delivers at the same time the expression for truncation error. Next, I'll explain another important approach to approximation of derivatives based on polynomial fitting. We'll concentrate here on first and second order approximations of the first and second derivatives. Higher order approximations will be the topic of the next lecture. Another important topic over which some controversy exists in literature is the order of approximations on non-uniform grids. Some approximations of second order obtain a first order term in truncation error when the grid is non-uniform. We shall see that if a non-uniform grid is systematically refined, the convergence remains of second order. This will be proven both via theoretical analysis and in numerical experiments. Finite differences were used by Euler in 18th century to solve partial differential equations. It is the oldest numerical method for this purpose. Finite difference methods use conservation equations in differential form as the starting point. We shall deal here with the generic conservation equation for a scalar variable phi, which describes the balance of transport by convection and diffusion. Sources or sinks may be also present, but we assume here that these do not contain derivatives and thus do not require approximations. If source terms contain derivatives, as in the case with equations in most turbulence models, they can be approximated using the same methods described for derivatives from convection and diffusion terms. Finite difference methods are usually used with structured or block structured grids. We shall see in the next lecture series that this approach can, in principle, be applied to unstructured grids as well. In this method, we need to approximate derivatives at grid nodes in terms of variable values at that grid node and some neighbor nodes. This results in one algebraic equation per grid node with variable values at that node and some neighbor nodes as unknowns. For the whole solution domain, a system of algebraic equations results. It can be solved if appropriate boundary conditions are applied to solution domain boundaries. This plot shows examples of a one-dimensional and a two-dimensional structured grid suitable for application of finite difference methods. The grids are non-uniform, expanding in x and y direction. Black symbols denote boundary nodes where boundary conditions are specified. Open symbols denote internal nodes where transport equations are discretized. The location of each grid node is uniquely defined by indices: I in x direction, j in y direction, and k in z direction, which is not shown in this plot. Let us first remind ourselves how is the first derivative defined in mathematics. It is the ratio of the difference in phi at points xi plus delta x and xi and the distance between these points delta x in the limit of delta x tending to 0. For a finite distance delta x and without this limiting instruction, this ratio represents a finite difference approximation of the first derivative. Mathematicians have proven that this approximation converges to the exact value of the first derivative at point xi. In this figure, we see a curve representing the variation of phi as a function of x. The first derivative of phi with respect to x at point xi represents the slope of the tangent to the curve at this location. The tangent is here denoted with the word exact. The above finite difference is represented by the line marked as forward. We see immediately that other similar approximations can be made. In one, we take the difference between phi at node xi and xi minus 1, represented by the line denoted backward. And in another, we take the difference between phi at points on either side of xi, represented by the line labeled central. We can now make two important observations. The first is that the line representing the approximation labeled as central is closer to the tangent labeled exact than the other two lines, representing backward and forward approximation. The second is that each approximation becomes closer to exact when the spacing between grid points is reduced. We can thus conclude that all three approximations become exact when the spacing between points used to construct the finite difference tends to 0. The variation of phi around location xi can be described by the Taylor series expansion given by this expression. It is an endless series and it is exact if all terms on the right-hand side are retained. An infinite series is not very practical, which is why we always truncate it after n terms. H denotes all terms of higher order. The retained terms on the right-hand side represent an approximation, while H represents the truncation error. If we in this expression replace x by xi plus 1 and rearrange so that the first derivative at point I is on the left-hand side and everything else on the right-hand side, upon truncation after the third term, we obtain this expression here. The part framed in blue represents the forward approximation from the previous slide. The red framed part is the truncation error for this approximation. In a similar way, replacing x by xi minus 1, we obtain the blue framed backward approximation with its corresponding truncation error. By subtracting the last expression from the previous one, we can obtain the following expression for the first derivative at point I. The blue framed part corresponds to the approximation given by the line labeled central in slide 6. The red framed part represents the truncation error. All approximations become exact if all terms on the right-hand side are retained. However, because high-order derivatives are unknown, the series has to be truncated somewhere. The leading term in the truncation error is usually the largest, because the next term involves grid spacing to a higher power, and for small spacings, the higher the power, the smaller the value. An exception is the unusual situation when the next higher derivative is much larger, which is unlikely. The exponent of mesh spacing in the leading truncation error term represents the order of approximation. It tells us about the rate at which the error reduces when the grid spacing is reduced. By using Taylor series expansion for more grid points around xi, we can eliminate some leading terms in the truncation error, one term per each additional grid node. Let us now compare the free approximation of the first derivative described in the preceding slides and their truncation errors. The forward and the backward difference are both first-order methods because the leading term in their truncation errors is proportional to grid spacing delta x. On uniform grids, the magnitude of truncation error leading term is the same, but the signs are opposite. We shall see in lecture 6 that indeed the results obtained with these two methods approach the grid-independent solution from opposite sides. One overpredicts and one underpredicts the correct solution. The leading truncation error term from central difference approximation becomes zero when the grid is uniform, because this difference in grid spacings on either side of the node I becomes zero. The next term is proportional to grid spacing squared on any grid, as can be seen in the longer truncation error expression shown in the preceding slide. This ratio is proportional to delta x squared. When the grid is non-uniform, the leading term is proportional to grid spacing delta x, and the approximation is apparently of first order. However, we shall see in slides 12 to 14 that when non-uniform grids are refined systematically, the error is reducing with second order. Note that the central difference approximation can be expressed as an average of the forward and backward approximations. This immediately suggests a much higher accuracy because the leading truncation error terms from forward and backward approximation have opposite signs, and thus in the average partially or completely when the grid is uniform cancel out. Approximations of derivatives can also be obtained by assuming a certain variation of the function to be differentiated in the vicinity of the point at which the derivative is to be computed. We shall deal here only with the assumption of a polynomial variation called polynomial fitting, but the assumed function can also be a spline, a trigonometric function, or something else. Here is an illustrative example. We assume that the variable phi varies quadratically with the coordinate x. For the sake of simplicity, we set the local coordinate system at the node I, where the derivative is to be approximated. We now have to fit a parabola given by this expression to variable values at three nodes, that is, obtain the three coefficients of the parabola such that it passes through variable values at three nodes, I minus 1, I, and I plus 1. Assuming a uniform spacing of grid nodes, these relations hold in the local coordinate system. x equals 0, xi plus 1 is equal delta x, and xi minus 1 is equal minus delta x. Forcing the above polynomial through the function values at three nodes leads to this system of three equations with three unknowns, the coefficients a0, a1, and a2. Note that the function values at these nodes are in general not known. The coefficients will be expressed in terms of function values phi I plus 1, phi I, and phi I minus 1. The coefficient a0 is equal to the variable value phi I because the local coordinate x is 0 there. By adding the second and the third equation, we eliminate the unknown a1 and can express the coefficient a2 in terms of variable values at the three grid nodes, shown here. Inserting this expression into one of the last two equations leads to the expression for the coefficient a1. Now that we have all three coefficients of the polynomial, we can easily obtain approximations for both the first and the second derivative. We first differentiate the polynomial analytically, and then in the analytical expression for polynomial derivatives, insert the local coordinate value at node I, which is here 0, and the expressions for the required coefficients. At node I, for x equals 0, the first derivative equals to the coefficient a1, and the second derivative is twice the coefficient a2. The approximation of the first derivative is the same as the central difference obtained earlier from Taylor series expansion. The same approximation of the second derivative can also be obtained from Taylor series expansion and is also called central difference approximation. If we repeat the same procedure of fitting a parabola to variable values at three nodes described in the two preceding slides to a non-uniform grid, the following approximation of the first derivative is obtained. The multipliers of variable values at nodes I plus 1, I, and I minus 1 are now not integer numbers as when the grid is uniform, but are functions of grid spacing. It will be shown in an exercise in lecture 6 that this is a second-order approximation of both uniform and non-uniform grids. Non-uniform grids are used to achieve a more uniform distribution of errors by using larger spacing where discretization errors are small. Many approximations lose the first term in truncation error when the grid is uniform, as was the case with central difference approximation described in slide 8. One may ask the question, is the order of approximation really lower when the grid is non-uniform, as it formally appears to be? We shall answer that question in the next two slides. Let us now analyze in detail the truncation error of the central difference approximation presented in slide 8. We are interested in the behavior of the leading truncation error term, here framed in blue, when a non-uniform grid is systematically refined. We assume that the grid spacing is expanding in x direction with a constant expansion factor Re, as shown here. The same conclusion results if grid spacing is reducing with a constant factor. For the sake of compactness, the following shorthand notation is used. Delta xi plus 1 is xi plus 1 minus xi, delta xi is xi minus 1. The grid spacing to the right of node I equals grid spacing to the left of node I times the expansion factor Re. When this notation is introduced in the above expression, the leading truncation error term becomes this expression, shown here. We see that the leading truncation error term is proportional to grid spacing, delta xi, multiplied by 1 minus Re. This looks like a first-order term, but the role of the multiplier is not obvious. To see the real behavior of the leading truncation error term with grid refinement, we need to check the ratio of these terms on two grids. Let us now consider a coarse grid with a representative spacing 2h, shown here. This grid is systematically refined by inserting another grid point between two grid points on the coarse grid, as shown on the lower side of the grid line in this figure. The location of the new grid point is selected such that we again obtain a grid in which the spacing between two grid nodes is equal to the spacing between two preceding nodes times a constant expansion factor, as was the case on the coarser grid. But when we double the number of spacings over a constant distance, the expansion factor on the finer grid equals the square root of the expansion factor on the coarser grid, as shown here. The ratio of the leading truncation error terms on the coarse and the fine grid, shown here, can, with this shorthand notation, be rewritten as follows. This ratio is on finite grid spacings greater than 4. It converges toward 4 as the expansion factor tends toward unity. The reduction of truncation error by a factor of 4 with doubling the number of subdivisions between boundaries is the property of second-order approximations on uniform grids when the error is proportional to grid spacing squared. The above analysis shows that if non-uniform grids are systematically refined, we obtain a second-order convergence even though the leading truncation error term appears to be proportional to delta x. We have already seen in slides 10 and 11 how one can apply polynomial fitting to obtain approximations of both first and second derivatives. A few more options for approximations of the second derivative will be described in this and the following slide. One can obtain an approximation of the second derivative by applying approximations of the first derivative twice. One may use a different approximation in each step. For example, we can first use a forward difference as in this expression. The first derivative at node I plus 1 minus the first derivative at node I divided by the distance between these two nodes. For the first derivative at node I plus 1 and I, we may use backward differences, as shown in these two expressions. By inserting approximations from the second step into the expression from the first step, we obtain the following expression for the second derivative. It involves variable values at nodes I plus 1, I and I minus 1, and distances between these nodes. One can show that this approximation is of second order. The first order truncation errors from forward and backward approximations in the two steps cancel out. If we use central difference approximations in both steps, we obtain an approximation which involves 5 nodes from I plus 2 to I minus 2. Such approximations are cumbersome and are difficult to apply near boundaries. The most widely used approach is to apply central differences in compact form, using auxiliary nodes between grid nodes, as shown in this figure. In the first step, we build a central difference by using first derivatives at auxiliary nodes I plus 1/2 and I minus 1/2. In the second step, we build central difference approximations of the first derivatives at auxiliary nodes as we would do on a twice finite grid. The resulting approximation of the second derivative at node I is given by this expression. It will be shown in the next slide that this is a second order approximation. The central difference approximations from the second step are of second order because auxiliary nodes are placed midway between grid nodes, and these approximations are of second order on a uniform grid. The approximation from the first step is a central difference on a non-uniform grid, but as it was shown in slide 14, it also converges with second order. Approximations of the second derivative can also be obtained using Taylor series expansion. Applying the expansion at nodes I plus 1 and I minus 1, as shown in slide 7, we can eliminate the first derivative at node I and obtain the following expression for the approximation of the second derivative and the leading truncation error term. The approximation is the same as the one obtained via a different route in slide 16. The leading truncation error term, which apparently is proportional to delta x, vanishes when the grid is uniform. The next term is proportional to delta x squared, so the approximation is of second order on uniform grids. However, we can use the same approach as in slides 13 and 14 for the approximation of the first derivative by central differences on non-uniform grids to analyze the behavior of the above leading truncation error term with grid refinement. I am skipping the derivation and show only the final result. The ratio of leading truncation error term on a coarse grid and on a systematically refined grid is greater than 4, thus confirming the second order convergence. For this conclusion to hold, the grid needs to be systematically refined. That is, the new grid points must be inserted between coarse grid nodes such that again a constant expansion factor results equal to the square root of the expansion factor on the coarse grid, as indicated in this figure. If the diffusion coefficient gamma is constant, diffusion term in the transport equation contains the product of the diffusion coefficient and the second derivative of the variable phi. However, if the diffusion coefficient is not constant, then the diffusion term involves the derivative of a product of two variables. See the left-hand side of this expression. We can perform first differentiation by parts to obtain two terms, as shown on the right-hand side. The first term accounts for the effects of diffusion coefficient variation, while the second term is the same as in the case of a constant diffusion coefficient. These two terms can be discretized using approximations for the first and second derivative described in preceding slides. It is desirable to use approximations of the same order for each term. Another option is to use the two-step procedure described in slide 16. To this end, we only need to interpolate the diffusion coefficient to the auxiliary locations I plus 1/2 and I minus 1/2. Because these lie midway between grid nodes, a simple averaging is a suitable second-order approximation. The first derivatives are approximated the same way as when the diffusion coefficient is constant. Approximations of inner derivatives are of second order because the auxiliary points are midway between grid nodes. The approximation of the outer derivative has a first-order leading term in the intrication error, but it converges with second order also on uniform grids, as shown in slides 13 and 14. I now want to show to you how one can check the order of an approximation by performing numerical experiments. For this purpose, I have written a small computer program which computes numerical approximations of derivatives at x equals 0 on systematically refined grids, using variable values at grid nodes taken from an analytical function. In this exercise, the following function is used. Phi is equal cosine of 3.2 times x minus 0.1. This plot shows graphically how the function, its first derivative and its second derivative vary between x equal minus 1 and x equal 1 meter. Discretization errors are computed by comparing the approximations of derivatives obtained using the exact value of the variables at grid nodes and the analytically computed derivative at x equals 0. We first check the backward, forward, and central difference approximations for the first derivative on uniform grids. Here are the excerpts from the computer code showing the expressions for derivative approximations: backward, forward, and central. The figure on the left shows the exact value of the first derivative at x equals 0, 1.006613, and the variation of numerical approximations by backward difference denoted BD, forward difference denoted FD, and central difference denoted CD, as the spacing between grid nodes, here labeled dx, is reduced. All approximations converge monotonically toward the exact value, except for backward difference on the coarsest grid. While the curve representing the central difference approximation cannot be distinguished from the line representing the exact value when delta x is smaller than approximately 0.1, there is still a significant difference between forward and backward approximations even for the smallest grid spacing used. The plot on the right shows the variation of the error with grid spacing on a log-log scale. The forward and backward differences are obviously first-order approximations because the slope of the line asymptotically becomes equal to unity. That is, when the grid spacing is reduced one order of magnitude, the error is also reduced one order of magnitude. The central difference approximation is of second order because the slope is 2. That is, when the grid spacing is reduced by one order of magnitude, the error is reduced 2 orders of magnitude. Even for a medium grid spacing, the error from central difference approximation is an order of magnitude smaller than the error from either first-order approximation. For the smallest grid spacing, the error from central difference approximation is more than 2 orders of magnitude smaller than the errors from forward and backward difference approximations. Let us now see what happens when the grid is non-uniform. On the coarsest level, the grid spacing to the left of grid node at x equals 0 was 0.781 meters and to the right 1.105 meters. The expansion factor equal to square root of 2. The grid is then refined by inserting new grid nodes such that the expansion factor remains constant and equal to the square root of the expansion factor at the next coarser grid, as shown in this figure. In addition to the simple central difference approximation, which ignores grid non-uniformity, given by this expression, the formula derived by fitting a parabola to variable values at free grid nodes, given by this expression, was also used. The figure on the left shows the exact value of the first derivative at x equals 0 and the variation of numerical approximation by backward difference, denoted by BD, forward difference, denoted by FD, simple central difference, denoted by CD, and central difference from polynomial fitting, denoted by CD poly, as the grid spacing dx is reduced. Forward and backward differences behave as on uniform grids. Both the simple and the more sophisticated central difference approximations converge fast, the approximation derived from polynomial fitting being closer to the exact value. The plot on the right shows the variation of the error with grid spacing on a log-log scale. The forward and backward differences are obviously first-order approximations, while both central difference approximations converge with second-order. This numerical experiment confirms the analytical analysis from slides 13 and 14, showing that the simple central difference approximation is converging with second order on both uniform and non-uniform grids. The experiment also shows that the more sophisticated approximation, which takes the grid non-uniformity into account, does lead to a slightly more accurate solution on every grid, but the rate of error reduction is the same as in the case of the simple approximation. Let us now check the order of approximations of the second derivative. This expression defines the simple central difference approximation, which assumes a uniform grid, while this expression here considers grid non-uniformity. The experiment was conducted for uniform and non-uniform grids as described in the preceding slide. This figure shows how the approximations vary with grid refinement. The green line, labeled CD uniform, shows the results from the simple expression when the grid is uniform, while the blue line, labeled CD uni non, shows the results from the same expression applied to non-uniform grids, whereby the mean of the grid spacing to the left and to the right of node I was used as delta x in this expression. The red line, labeled CD non-uni, shows the results from this expression applied to non-uniform grids. This figure shows the errors from approximations on each grid versus grid spacing plotted on a log-log scale. We see that the simple approximation applied to uniform grids and more sophisticated approximation applied to non-uniform grids converge with second order. When the grid spacing is reduced by 1 order of magnitude, the error is reduced 2 orders of magnitude. This confirms the analysis from slide 17, where the second order convergence was predicted even though the approximation contains formally a first order term in the leading truncation error term. The simple approximation applied to non-uniform grids converges to a wrong value of the derivative as the grid is refined. Finally, let us check the order of approximations of the diffusion term when the diffusion coefficient is not constant but varies linearly in x direction, as indicated by this expression. One approximation is based on differentiation by parts, as shown by this expression. The diffusion term has then two contributions: the product of the derivative of the diffusion coefficient with the first derivative of phi, plus the product of the diffusion coefficient at x equals 0 with the second derivative of phi at the same location. In the second approach, the inner derivative of phi is approximated at auxiliary points midway between grid nodes and multiplied by the interpolated value of the diffusion coefficient. The outer derivative is then approximated with the central difference, as described in slide 19. This figure shows the variation of the derivative from different approximations, while this plot shows the errors from approximations on each grid versus grid spacing plotted on a log-log scale. The green line, labeled CD uniform, shows the results from this expression when the grid is uniform, while the blue line, labeled CD non-uni, shows the results from this expression applied to non-uniform grids. The red line, labeled CD non-uni 2, shows the results from this expression applied to non-uniform grids. The blue and the red lines lie exactly on top of each other and cannot be distinguished. The convergence is of second order on both uniform and non-uniform grids. This is a brief summary of the lecture on principles of finite difference approximations. We have seen how finite difference approximations of first and second derivative can be derived using Taylor series expansion and polynomial fitting approaches. Taylor series expansion is always used if one wants to determine analytically the order of an approximation. However, the order can also be determined using numerical experiments, as described in slides 20 to 24. The order tells us at what rate is the error reducing when the grid is refined, not how large the error on a given grid is. Methods of the same order can have errors that differ by as much as an order of magnitude. Some approximations contain a first-order term in the truncation error when the grid is non-uniform, but the errors are still reducing with second order on systematically refined grids.